Hello, Internet. This is your captain speaking, Lester Nare, joined as always by my co-host and our resident PhD, Krishna Choudhary. My friend, how are you?
Pretty good.
You have any exciting Thanksgiving plans for the week?
Yeah, I'm gonna go to Maui with my
life.
parents. It's gonna be great.
That's
yeah.
awesome.
Yeah. Hopefully I'm gonna get to see the Daniel K. Inouye telescope.
I was actually going to ask
Which
if
is
you're going to make a trip out to the
Yeah. We're
observatory.
definitely gonna make a trip out. I don't know if the telescope is operating, but it'd be nice to see whatever I can.
Absolutely. And it's an interesting dovetail, at least on the observatory piece for the story we're going to spend a lot of time on today, which is we're going to talk about 3i Atlas. We now have the observations.
Yep.
We've had time to put it together. We did touch on this once before.
Yes.
So we're doing a little bit of an update based on all of the latest and greatest. It's been in high demand. We're going to start off with 3i Atlas today, followed up by a new story that's going to be out of Maynooth University in Ireland. It was in forensic chemistry around a new technique for taking fingerprints off of fired bullet casings. So this is a new forensic technique that will help us catch the bad guys even better. Ending with a new Alzheimer's sort of discovery around microglia or immune cells that are in our brain.
Yeah.
This is a combination of a couple of universities in nature, Icahn School of Medicine at Mount Sinai, Max Planck Institute of Biology and Aging, and the University of Cologne. So 3 incredible stories. We're going to touch on all the details.
Yep.
This is From First Principles. So our first story of the day is 3i Atlas.
Yes.
This is the one that obviously everyone keeps asking us about because the government is back open.
Yeah.
And so NASA has now released new imagery.
Yes.
So let's sort of just start right from the top here.
Yeah, I mean it's a interstellar visitor, as we all know. It's the third interstellar object. There's been 2 predecessors that it's had. The first one was Oumuamua. The second one was 2i Borisov, and this is the third and the largest one that we have by far. Okay. Oumuamua was a really strange one. It was an inert, highly elongated object that was flying through. Then we had 2i Borisov, which was basically just like a normal comet, like any other comet that we'd seen. The only thing that was really different was that it was moving so fast that it wasn't trapped by the sun's gravity, right? And then now we've got finally this guy, 3i Atlas. The I stands for interstellar. The 3 stands for the fact that it's the third. And the Atlas stands for the fact that it was discovered by the Atlas system, which is the Asteroid Terrestrial Impact Last Alert System. These are a bunch of telescopes all over the world. The one that actually discovered this was in Chile. And the whole point of this telescope system is to find near-Earth objects or objects that are coming through and going to be a little bit close, right, in our solar system.
Right.
It preferentially looks in the plane of the planets.
Okay.
Right? So
Meaning,
if the sun is here, all of the planets revolve around the sun in the same sort of plate, right? It's not like the Big Bang atom.
Okay.
From the show where it's like,
show.
There's one going this way, there's another going the other way. They're all sort of along the same plane.
Makes sense.
Right?
Yes.
And that's because when the solar system first formed, there was some angular momentum of that cloud. So when it collapsed, everything has to be on that plane to preserve the angular momentum.
Makes sense.
So that's actually why we discovered this thing. And one of the reasons why it's sort of taking a tour of the planetary systems, right? It's kind of by design that Atlas finds objects that are along this plane, right? So it begs the question, there might be other objects that are not in the plane that we're not really sensitive to.
Right.
But perhaps with the new Vera Rubin telescopes and things like that, we will be. But in any case, that's how it got its name, right? It's inbound. It's got an extremely hyperbolic orbit. So an eccentricity of approximately 6.2. The Earth is basically at a 1. It looks like a circle, right? But this thing is extremely hyperbolic. you can see that it's going so fast, 58 kilometers per second, that it barely even changes its orbit
as
it passes the sun, right?
Right.
Unlike the the Wicked movie, there's that one of my favorite songs is like a comet pulled from orbit as it passes the sun. This is not doing that. Yeah, it has not changed in any real sense, for the better or the worse. But it 58 kilometers per second, right? That's a velocity that's 3 times higher than what's expected for a usual star encounter.
So this thing's moving extremely quickly.
Yeah, and it begs the question, like, what even gave it its speed to begin with?
How did it reach that?
How does something move that fast through the solar system? And the orientation it's also retrograde. The other weird thing is, in the Milky Way, the sun is moving around the Milky Way, right?
Yeah.
And the plane of the planets is about perpendicular to the motion.
So our entire sort of solar system is moving through the Milky Way galaxy, like let's say on the X axis. But then the orbit of the planets in that context, while we're doing that, is on the Y axis.
Is in this Y,
like Y
right?
direction.
And so when 3i Atlas, when we say that it's taking a tour of the solar system, what it's really doing is it's like piercing through the Milky Way in some sense, right?
Mm-hmm.
It's not moving. I mean, obviously it has some direction along the Milky Way's rotation as well, but it's going through the plate of the Milky Way as well. That's why it's going through all the planets in the plane of our ecliptic,
which is sort of a cosmic the cosmic serendipity there is quite
and it's kind of a mystery where it came from and things like that, and we're going to get into some of that later. So there's been some milestones that have happened since the last time we talked.
Mm-hmm.
It flew by Mars on October 3rd, 2025. That was when it got as close as it possibly could. And that was a really cool way of providing a local observation, right? Because we have the Mars Reconnaissance Orbiter around Mars. The ESA, the European Space Agency, has a bunch of stuff around there. And it's about 28 million kilometers away from these guys. So you can get at least some close-ups. It's still far away.
28 million kilometers.
Yeah. It's close enough, right?
Yep.
And then on October 30th, 29th, it had its closest approach to the sun, which was at a distance of 1.36 astronomical units.
Yep.
1 astronomical unit is the orbit of the Earth. So it didn't even get closer than Earth is to the sun.
Got it.
Okay. A lot of comets, the really bright ones get within Earth's orbit, sometimes even like as close as Mercury.
Right.
As close as like between Venus and Mercury. And those are the ones that glow and you can see with your naked eye. This one, not so much, right? It wasn't that close. And then finally, in December 19th, it's going to be well outside the Earth's orbit, but that's when it's actually going to be the closest to Earth. It's going to be 80% of the distance between Earth and the sun, but it's going to be in the other side.
Yep.
Right? So the sun will be in front of us, the comet will be kind of behind us.
Mm-hmm.
But that's when it's going to get closer.
Okay.
So I told you that it's got a really weird orbit, right? It's coming through really fast, and it's going along the plane of the planets. It's unclear whether it's coming from a part of our Milky Way called the thin disk, which is really what you see when you look out in the night sky and you see the Milky Way, or from the thick disk. Because if you trace back, the yellow trajectory here shows where the comet is, and the red trajectory is where we are, where the sun is. And it's sort of like playing tag and go with our sun, because it's about the same distance away from the center of the Milky Way as we are. And so it's going to be kind of sharing our orbit. The same way that, you can imagine the Trojan asteroids outside of Jupiter, they share the same orbit with Jupiter and they move around with Jupiter. The James Webb Telescope is orbiting the sun with the Earth, right? Because it's feeling the same gravitational pull from the sun that the Earth is and the moon is. So the question is, where did it come from?
The idea is, as we are traveling through the Milky Way, we're going on a particular orbit, and the way that 3i Atlas moves through the Milky Way is in that similar circular orbit
Exactly.
In the radius of that orbit is almost identical.
It's almost identical, right? I mean, hence it's right here.
Right.
And the Milky Way has a gravitational potential because of all the stars and gas in it.
Yep.
And the sun is feeling the same gravitational potential that the comet is.
Yep.
And because of Newton's law of gravitation, the acceleration that we feel is independent of our mass. So even though the comet 3I Atlas is really, really small compared to the sun, all objects fall at the same rate, according to Galileo, right?
Yeah.
So it doesn't mean, like, in terms of the orbit, it's not really going to matter if it's the sun or a star, right?
Yep. That's a good distinction.
That's the point.
Yep.
That's why the James Webb Telescope is moving around the sun the same way that we are.
Right. Even though it's obviously smaller
than the Earth, right? So the first paper that tried to answer this was from Oxford in the Astrophysical Journal, Letters. This was in July, and they said that it's from the thick disk. The thick disk is the part of the Milky Way that's just above all of the stars and the real gas. So the stuff that we see in the night sky when we look up, that's the thin disk. The thick disk is the part that's right above or below. That's an old population of stars. We know that because we can look at the spectral signatures of the stars that are above there. And, there are these very red, long-lasting stars with lots of metal, which means they've been doing fusion for a while. It depends, actually. It depends on whether it's high metal or low metal. High metal could also mean that you're the second or third generation of stars that are coming from the ashes of the older stars that have made the metal. And then low metallicity could mean that, okay, you just have hydrogen and helium. So it's like from the Big Bang. You got nothing else, But so there's ways of quantifying it. But in any case, they've quantified that a lot of these stars are between 7 to 14 billion years old, right? So it's much older than the sun, which is about 5 billion years old, right?
Right.
So that was the first one. Then there's some new work that came out in September. This is not in a journal, but it's on the archive. And it was from the Tenerife Observatory, a bunch of people there in Spain. They were trying to trace back the object's origins in a similar way. And they showed that they used this Python package called Milky Way Potential 2022, which basically what it can do is it can take your object and then run back the clock for however long that you want, given the Milky Way potential. And what they found was that if you integrate over the millions of stars in that database and you go back, at least in the last 10 million years, there's no close encounter that's going to cause this giant velocity. Okay? If you go through all of and those are the stars that that it had close encounters with.
Yep.
And none of them were close enough to really add any velocity to this thing.
The point being, 3I Atlas had to get its acceleration from an encounter with some celestial object at some point in its history.
Yeah. But it can't be the recent history.
Yeah. Okay. And then when we look in this Milky Way Potential 2022 and trace back the journey that it had made and the stars that it would have passed, these celestial objects would have passed on the way, none of those are of sufficient mass and size.
Yeah, and it wasn't close enough
to generate the acceleration that we're seeing. That's what the paper's trying to say.
That's what the paper is trying to say, right. So then they say, okay, what we can do is we can really just run back the clock, right? And we can say, okay, if it's not in our recent history, let's just treat the Milky Way as this like potential landscape and ask, how far does it deviate away from the thin disk, right? Because what it could do, what the original paper was saying was that, because it's got such a high velocity perpendicular to the disk, it must be coming from up there.
Yeah.
Right? But the potential landscape is such that when it goes above the disk is going to start pulling back. And so there's going to be some oscillation through the disk, right? It's going to go up. And then it's going to come back down, and it's going to go down, then it's going to get pulled back up again.
Yes.
Right? So how big is that amplitude?
Right.
Of that oscillation?
Basically, how high, how far above and below the thin disk?
Yes.
Is it
going, right? Is it going all the way to the thick disk? Because we also have velocity profiles of the stars that are up there. There's some typical trajectories that those guys take, and there's some typical trajectories that the thin disk takes. Which one does this thing belong to?
Got it.
Right? And so that's what they did. And what they think is happening is that it stayed basically within the thin disk, and they're ruling out the fact that it could be in that upper thick disk.
Okay.
They found where the velocity profile of this comet is compared to the stars in these two regions, and it's more aligned with the thin disk.
Interesting.
Right?
Okay.
So this is kind of a clapback to the Oxford paper.
Which was that original
one. So we're going to have to see if Oxford comes back and says, nah.
This is good because when we first covered this, the Oxford paper was the only one.
The only one, and everyone was like, okay, that's got to be it.
Right.
But the process of science is extremely dynamic. There's a bunch of researchers vying for the spotlight.
Right.
So, someone's gonna say this, the other person's gonna say that.
This is very good. So we now are in a position in terms of the locational origin of the 3i Atlas, which initially was believed to be coming from above where we are on the thin disk in the thick disk, but there's at least now a rebuttal.
Yes.
There's at least now a rebuttal to that can explain away the thick disk origin hypothesis.
Yeah, exactly. And now it calls into question whether it is as old as they say they are. Because it used to be, we were really excited, right? This is going to be the oldest thing in the solar system.
Right.
It's going to be older than 7 billion years old because all of the stars that are up there are super old. And if it came from there, then it's got to be super old too. Now, well, if it's just one of these thin disk populations that just got bumped maybe a long time ago, right? It's no longer maybe that old.
Right.
Maybe it is quite contemporary.
Yep.
So there's a bunch of, very cool science that is still happening, trying to figure this out.
Trying to trace back its location, origin location.
Yeah. So that's the origin story. It's still in question.
Yes. Okay.
Now let's talk about what it actually is and why it is so interesting. It is quite a bizarre comet. Okay. If we're completely honest, there's a typical comet that we see in our solar system, and this is a pretty bizarre one. It's not unprecedented. We have seen comets that do the weird things that this thing is doing, but it's been like one or two.
Got it.
Okay. So it's rare, but it's not like totally unprecedented.
Yep.
Okay.
Yep.
So it's got a nucleus. The radius is about anywhere between 0.22 kilometers to 2.8 kilometers. That's how we constrained it. There's a lot of activity on this thing. It's called a hyperactive comet. Okay. As the comet gets closer and closer to the sun, the solar radiation and the photons from the sun start creating chemical reactions and physical reactions on the comet's surface. And that's going to just make it glow and do all of the cool things that it does. And a lot of the weird stuff that it does it's been implied that, maybe there's something weird going on, if there's a techno signature, blah, blah, blah. A lot of this actually came from Avi Loeb at Harvard.
Right.
But then in October of this year, he came out with this model, which is a physical model for the ice coma of 3i Atlas with Avi Loeb and one of his collaborators, Eric Quito. And this one is trying to suggest how the physics of a comet could produce all of the weird stuff that we're seeing. Just normal comet, maybe not a normal comet, but kind of a weird comet, but just ordinary physics.
Right.
Stuff that we know.
Right.
Okay, one of the things that it tries to explain is something called the anti-tail. This was very weird, right? There was if you can see over there, this is from the Hubble Space Telescope. On the right is where the sun is, and there's some projection. There's like a jet from the comet coming out towards the sun,
which is counterintuitive, because the idea would be if the comet is traveling at high velocity towards the sun, you would imagine the quote unquote jet would be pointing in the opposite direction.
And there is one. Yeah, and there is one. There is an anti-sun tail. And because of the way that we're looking, right, it's coming at us. So the anti-sun tail is kind of behind the comet, and the sun-facing one is towards us.
I get that.
Because of our vantage point, it looks like the sun-facing emission is that much brighter, but that's not actually true. But in any case, there is a sun-facing emission, right?
Okay.
And then when it went past post-perihelion, so it went past the sun on the other side. Now there's no anti-sun tail. Sorry, now there's no towards the sun tail. There's only the anti-sun tail. Okay, so it disappeared. This is from the Very Large Array, the Very Large Telescope, the VLT in Chile. So the nucleus has done this thing where it had jets pointing in both directions.
Yes.
And then on the other side of the sun, it no longer has that.
Yes.
So what's going on? The model that Quito and Loeb proposed is the following, okay? So when the comet is coming towards the sun, there's going to be something called sublimation. Sublimation is what happens with dry ice, where you go directly from a solid form to a gas form. There's no in between of liquid because the temperature, the energy is enough to cause the CO2 molecule to just free itself from the gas, not transition through that liquid phase. Now, when it's happening and it's coming towards us, that sublimation is actually going to cause chunks of CO2 to sort of shoot out from the comet. Okay? And if you're far enough away, those chunks of CO2 are going to shoot out, but they're going to follow with the comet because of the same thing that I said earlier, right? They're falling towards the sun the same way the comet is, even though the comet is this giant mountain of stuff.
Yes.
And let's say a chunk of CO2 is, centimeters to meters to maybe tens of meters big. That thing is still feeling the sun's gravity, so it's going to follow in the same sort of path, but maybe a little bit ahead because it got shot towards the sun.
Yep, got it.
And the solar radiation out there, far away, is not enough to quickly melt these chunks, okay? So it's sort of like the comet is here, you've got these chunks of CO2 ahead, and it's moving along the sun, right?
Yep.
Now, as it gets close to the sun, there's going to be so much pressure, radiation pressure and ionization pressure, that these chunks, as soon as they get out of the comet, they're just going to immediately evaporate. And so that's why we're seeing that loss.
Yeah, that makes sense. Yeah.
Of the front-facing tail, right? Because the closer you get, the more the shorter the lifespan of the stuff that's getting ejected.
At distance, we're seeing these large chunks break off, right? But they're in such large size, and the pressure's not high enough yet that they maintain its structure.
Yeah, and they just follow along.
Right. At this slightly, again, because it's basically getting broken off from the front side as it's making its way over. But as you get so close, the heat, the radiation is so high that the lifespan of that tail that is appearing in front doesn't have enough time to exist before it evaporates into going from that sublimation process, going from solid to liquid, which, if I recall correctly, was also part of the original walkthrough we did about where the origins of this could have been, where it could have been around a star that had this accumulation of icy things, and then it broke up. So there, in that first episode, it's interesting that same process was discussed well before even this Quito-Loeb paper came out.
Yeah, and that was in how it formed. It formed in the snow line, in that ice line, right? Where the CO2 goes from gas to being able to freeze. So there's a bunch of frozen stuff right at this ice line, and maybe the comet formed there, which is why there's so much CO2 compared to water. And it's basically the opposite process on the formation. Now we're seeing it. Now we're seeing it on the other
side.
And
so if you go back and watch that episode, it does a good job. We go into detail about the concept of sublimation and that formation process that actually kind of dovetails to what you just talked about quite nicely.
Exactly, yeah. So that's sort of the Quito-Loeb hypothesis,
right?
For why we're seeing a tail sometimes and not other times.
The sunward extension, specifically being the thing that was weird.
Okay. Yeah. So I wanted to highlight that paper because I thought that was a quite interesting physical model.
Yep.
That's out of Harvard Astronomy. So now let's get into some of the observations that have been happening.
Yes.
So the James W. Space Telescope, infrared chemical fingerprinting. So this is in the infrared range. The space telescope took that photo. The coma is highly dominated by emission that's coming from CO2 and H2O.
Yep.
And one can see that the mixing ratio between the CO2 and H2O is 7.6, which is way higher than the typical solar system comets, right? The typical solar system comets are at 0.1 to 0.2. 3i Atlas is all the way up there.
So we're looking at this it's
graph.
It's a plot. And then we see basically that 3i Atlas is well above
The trend line.
The trend line. Well above the trend line.
There are a few that, like the C2016 R2, that's another comet that's local, and that's even more above than 3I Atlas. But these are exceptions. That's the point.
Yes.
These are very much exceptions. And the fact that, we've had 2 interstellar visitors, one is typical, the other is crazy. Yeah. Of course, like N equals 2 is a very small sample size, but it begs the question, are most interstellar comets atypical? Right. It's kind of an interesting question because we don't know where they formed and how they formed, around what stars they formed and things like that. The other thing that's kind of weird about 3I Atlas is there's a lot of nickel and there's not a lot of iron. This is very strange because those two usually come side by side together. Okay? They're formed at the core of stars during explosions, things like that. And one can imagine that whenever they form in a dust cloud and they're in some environment, they have typically the same kind of elemental mass. So they're going to be forming together. It's not unprecedented again, but it's definitely unusual. That there's a lot of nickel, there's not a lot of iron.
The ratio between these two is so... the delta is so large.
Yeah. So that, again, there's another question mark there. How did you get a lot of nickel on a comet but no iron?
So we one of the questions is like the velocity question, which goes to origin. One of the questions is the
CO2,
the sunward extension CO2 piece.
Yeah,
and then this is now like the like a third question, which is the composition itself.
Yeah,
just to try to like quickly summarize those 3 key points that are quote in question.
Yeah. Okay. Exactly. Okay. Another really cool local view that we got, I was telling you about the Mars fleet that we had.
Yes.
So the MAVEN probe, which is on Mars, imaged 3I Atlas. We found a massive neutral hydrogen corona using the Lyman alpha line, which is one of the spectral lines of hydrogen that this MAVEN instrument actually had access to. So from that, we can actually derive a water production rate, and there's a lot of water sublimation that's happening on that comet, okay? Which is kind of cool, but that's not really that unprecedented. Comets have a lot of water. It used to be thought actually that, and it still is thought, that a lot of the Earth's water came from comets, because when Earth was forming, probably all the water just got evaporated, and then comets came and deposited their water during the early bombardment of Earth when it was forming. And one can actually look at the isotopic ratios of different isotopes in water in comets and in the ocean, and they're the same. So that suggests that there is a link. The last piece from Mars that I want to highlight is the Mars Reconnaissance Orbiter HiRISE. This confirmed that there is a nuclear diameter, which is probably less than 30 kilometers. That's the limit of the high-resolution imager. I mean, we've had tighter constraints before. Actually, I saw an interview of Avi Loeb on like NBC where he was just like, this like, there's nothing new here. Like, the data kind of sucks. Like, it's like, I mean, give them a break. They were supposed to image Mars with this thing. They didn't know that they were gonna have like a comet on their hand that's like astronomical unit away. But I just thought it was funny because like everybody's like really excited about this data, but because the orbiters around Mars are built for Mars, right? As like, within hundreds of kilometers to thousands of kilometers, now you're asking them to image something that's 30 million kilometers away, that's much smaller than Mars. They're not going to have a good time.
This is an important sort of side note, because I think this has been the one thing that a lot of people have been like leaning on, which is like, we spend billions of dollars and like, why is it that, we can't capture imagery that is, equivalent to like this, and they just bring up an example of something else. And I think for the Mars orbiters specifically, it would be like asking you to take a picture of someone holding a penny on the Empire State Building from Los Angeles with your iPhone. And it's like it's not built for that.
It's not built for that,
maybe you could use a specialized tool to do so, but that just wasn't what was up there at the time.
Yeah, exactly. Like wildlife photographers use giant telephoto lenses,
to get those shots.
They spend thousands of dollars on that. They don't just all go up with an iPhone.
As someone who's had to take photos of my little brother at sports games, and having video lenses, not a telephoto lens,
there's a reason why the lens matters, and like it's a hardware problem at some point, right? The other really cool way of monitoring this thing was with something called Stereo A, which is solar conjunction monitoring. This is a really cool set of satellites we have on two sides of Earth's orbit that monitor the sun all the time. Because the Earth only sees the side of the sun that it's seeing.
Right.
What we'd like to do is see all of the sun all the time.
Right.
So what they do is, as the Earth is revolving around the sun, they have two satellites that share Earth's orbit, but are on 180 degrees away from each other. So they're imaging the sun from two different sides. One is leading the Earth, the other is trailing behind us. And so with this, we can actually track 3i Atlas as it goes behind the sun, right? Because when it was coming towards Earth, it actually went behind the sun and we could no longer see it. Well, with these two satellites, we can, and we can track it. And we were tracking it, and the object kept its structural integrity. Again, this thing is built for imaging the sun, not comets. But at least it could see that, okay, this thing still exists on the other side. It didn't like totally disintegrate like some comets sometimes do. And then finally, I want to mention that ISRO, the Indian Space Research Organization, did some observations with the 1.2 meter Mount Abu Infrared Observatory. I have actually been to that observatory because my dad used to work there.
Look at this guy.
Yeah, that's me when I was probably like 9 or 10 years old.
That's so awesome.
Taking a photo with that 1.2 meter telescope.
Yes.
So that was pretty cool that I saw that, one of these observatories that my dad did a lot of research at back when we were in India, did some things. They've got a really nice spectrometer there. So they found some key molecules in that spectrum. They found the swan bands, which are C2 and C3. That's 2 carbons and 3 carbons. And they also found cyanogen, which is carbon and nitrogen. Like, those bonds have very specific spectra. And from that spectrum, we can actually find that, okay, these molecules do exist. And it sort of refutes any lingering claims that there's some like inert or artificial composition, because again, comets are very typically have these kinds of carbon spectral lines. So that's sort of where we're at in terms of 3i Atlas, the current data, all of the current observations, not all of them. I mean, we still keep doing a bunch. There's a lot of actually amateur astronomers that are taking really great photos of this thing. Which I find really awesome. It's a weird comet for sure. Probably came from a metal-rich star system. That's why it's got a bunch of nickel. The fact that it doesn't have a lot of iron is kind of weird. But there's a lot of stuff that we can do with it, right? I'm really excited for the Vera Rubin Observatory that's going to come online. I'm also really excited for an ESA mission called the Comet Interceptor. It's this new type of mission where it's scheduled for 2029. It's designed for high-speed flybys, okay? And this thing is the highest speed possible, right? So now we've got sort of a parameter space on how high we think flybys should be capable of.
Right. Because we have a real-world data point now with the Atlas of knowing, like, okay, we are going to see objects that are moving this quickly.
And so now we need to meet those expectations of, okay, we found this thing in July, or in July we found it. We've got like a few months to scramble the fighter jets, to scramble the rockets, and get this thing going. That's the capability that we need in order to really study these things really up close. So now we have some data points to actually, give us that ballpark estimate.
It basically gives like a sort of a mission orientation. For the how fast do we need to set up a rapid response? And what are the sort of what are the keys to implementation in order to be able to accomplish it and do so? And I cannot wait I keep thinking about how with Vera Rubin, the number of these interstellar objects is going to just balloon and explode. If they are there to be discovered, it will be discovered.
It will be discovered by the Vera Rubin. 100%. The Vera Rubin would have discovered this thing, had it gone online 3 weeks earlier,
which is so crazy,
right?
It's so crazy, and would the quality of that data would have been fantastic. Again, this being a tool that is built for that type of observation.
Yeah.
In contrast to the Mars orbiters, which just happen to be closer in proximity and also able to see it at a time where we were on the other side of the sun. So very would not have been helpful during that window of time.
Yeah, definitely not.
Just that window of time. Fascinating. So jury's still out on origins.
Yep.
Locationally, like where it is coming from.
Yeah.
We have,
and thus jury's still out on age. Because location is tied to age.
So we still don't know like where and how old.
Yeah.
We have an interesting explanation for the sunward extension, but that still is being developed.
Yeah.
It's
again, that's on archive. That's not been peer reviewed and published.
Right. And we, don't quite have the explanation for the nickel-iron ratio.
No.
So these are still open questions.
Yeah.
Which is fair and understandable, and it's interesting to see the iterative
this
process.
thing's a few months old.
Right.
And right now we're still in the capture all the data you can. It's going it's in December. It's going to be close to Jupiter.
Right.
So that'll be interesting. We have some probes there that perhaps can go, orient and take a look. Well, I don't know what the plans are there.
I think what is interesting is it's it hasn't been clear, or we haven't had a lot of these, so we've never had the opportunity to say, hey, we have all these instruments in our solar system now, which we didn't have before.
No, yeah.
We have a ton of stuff that's just out there, and when there is these ephemeral events, these events that happen, in a moment in time, are these tools going to be used to capture this data or not? And this is like proof positive that like everyone understands the import and the unique opportunity and chose to do so. So another update on 3i Atlas. I'm sure we'll do another one.
Yep. Once it's all gone.
Once it's all gone and everyone's really doing that deep dive.
Yeah, or once it puts probes in Jupiter.
right. Apparently
we'll know in a month.
December 19th. It's still not done yet. So we're waiting for quote unquote whatever, December 19th. That was our story number 1, which was again a quick update on 3i Atlas. We're gonna now move on to story number 2, which is a very different context. We're going into a forensic story.
Yeah, we've never done a forensic story.
I was gonna say, I think it's our first. But
I thought this was really cool.
A true crime. So if you're a fan of true crime, you're gonna love this one.
Yeah.
This is out of forensic chemistry, research out of Maynooth University in Ireland for fingerprints from fired bullet casings. So I think the top line is there's a new technique that is making it more efficient to figure out who done it.
Yeah. And from fired bullet casings, which is really quite something, because it's kind of the holy grail of modern forensics, okay, is to find fingerprints from bullet cases that have already been fired, right? Because then you can tie a suspect to actually loading the gun rather than just possession of the firearm.
That's an important distinction.
Right? Yeah. That's pretty big.
Yes.
It's a really cool methodology involving electrodeposition. The paper is out in Forensic Chemistry by Maynooth University in Ireland. The fingerprints are typically destroyed whenever a firearm discharges, right? Because you have stuff like 500 degrees Celsius, pressures of 50,000 pounds per square inch. And this method exploits some organic residue that remains even after all of this stress, and it like amplifies that organic residue to create a fingerprint. And it's very cool that the electrochemical techniques that they're using to do this. Okay, and the significance is, as I was saying, right, the print on the casing links individuals to the act of loading the gun, and before we really only have the possession of the firearm. But somebody else could have done it. Somebody could have taken the firearm and done something.
Yep.
And the prevailing consensus is the violent process of actually firing a bullet would destroy the fingerprint on the casing.
Right. The theory of the case is you're never going to get the fingerprint off of the fired bullet.
Exactly. Yeah. And it is a pretty violent process, right? Of firing. I've fired a gun only once. I went to a shooting range, and it was like one of the craziest exhilarating experiences I've ever had. I've never done it again. I had to do a lot of research on how the gun works and the physics of the gun, but this is my 2-minute summary of the process.
Yes.
This whole thing happens in under 2 milliseconds. You've got a casing that has gunpowder, and then you've got the bullet, which is the projectile in the front. You've got a firing pin, and when you hit the firing pin with the trigger, that causes a chemical reaction which raises the temperature inside of the casing. All of that gunpowder or whatever goes up in temperature around something like you can get as much as 2,000 degrees Celsius. And then that's going to expand a lot of air, which is going to shoot the gun forward, okay? That's not the end, though, because afterwards, you have to take out the casing and replace it with the next one, right? So there's like a thing that grabs the case, pulls it back, throws it away, and then loads up the next one, right? So all of that stuff is going to mess with the fingerprint that's on the outside, because when the bullet is fired, that expansion of the air is also going to, first of all, it's going to heat up everything. So any organic residue that you have, like the proteins or any carbon, that's just going to burn up.
Burned off.
Yep. Then the casing itself is going to expand into the chamber, and when you pull it back, that friction is going to then again destroy any residue of a fingerprint that's on the outside.
Yep.
Right. So there's all of these different things that are happening that will completely mess with the fingerprint that's on the outside.
Right.
Okay. So the recovery relies on some persistence of like a decomposition product that's on the outside. Okay. And what this particular paper is focusing on is the carbonized ash. So there's going to be some inorganic salts that are left by our sweat and our oils that is going to remain. It's going to get burned up, but the ash is going to remain on the outside.
There's the idea being, the theory of the case is there's no organic residue that will be left after the bullet is fired because it's just going to get burned up.
Yeah, like the proteins, the oils, and the lipids, it's gone.
But their hypothesis was there's going to be a little indicator still left despite all of that.
Yeah. And it should be the burned up ash of all of that stuff.
Of all of that stuff.
Right? And there should be a little bit left. Right? And if there's even a little bit left, there's a chance.
You're saying there's a chance.
Exactly. And so that's what they're doing here. This isn't completely unprecedented, okay? So in 2008, there was a guy, Dr. John Bond. He came up with a mechanism to actually figure out these casings.
That's crazy that his name is Bond.
Yeah. And I thought it was like part of the Bond when I was reading it, because my summary just had Bond, and even the news articles about this just have Bond, and I'm like James Bond? like this is, maybe this is one of Q's like the weird techniques that he's made. But no, this is Dr. John Bond, and he came up with a way of using really high voltage, 2.5 kilovolts, right? And what you do is you realize that most of these casings are made out of brass, which is copper and zinc. Okay. And the zinc and the copper are going to react with the oils on my finger in different ways. Okay. So where the fingerprint was, that's actually going to create a chemical reaction and a corrosion of the zinc part, not the copper part. Okay. So there's going to be different resistance. There's going to be different tiny layer of different metals. And what I'm going to do is subject this casing to really high voltage.
People are crazy.
And then put a fine conducting powder on top. And then that powder is going to be attracted to the corrosion sites because that's going to be more conductive than the rest, right?
So
and then
brilliant.
I can make a fingerprint out of that.
That's so brilliant.
It's pretty brilliant. So in 2008, this has already happened. Right. This is going one step further. Okay. And
so we've identified that we can basically put like current into a substrate, and it will basically reveal this this pattern, which is the fingerprint we're looking for, because the zinc interacts.
The metal itself.
The metal itself interacted differently with the organic, residue, which is just us touching the outside of the brass bullet casing.
Yeah.
Where he's like, let's just pump it. And then it just shows up.
Yeah.
That's so, I know that's like a bastard, but that's so.
I think that's pretty cool.
That's pretty cool in and of itself.
Yeah. The problem is it works on brass because it requires this alloy, right, of copper and zinc.
Yep.
Well, now, I think there are now casings made out of steel, stainless steel, and things like that. It's not going to work.
It's not a universal
because the chemistry is not going to work with the iron.
Yep.
And the carbon that's in the steel.
Okay.
So, what these guys did was use a process called cyclic voltammetry. So you start with an electrochemical cell, which is a 3-electrode setup. You've got a working electrode. In this case, this is going to be our brass casing, the thing that we want to actually test on. There's going to be a counter electrode, which basically completes the circuit. And then there's a reference electrode that keeps the circuit at a certain voltage. And you've got, so imagine you take your brass casing, you put it in a chamber with a bunch of electrolyte around it, so chemically conducting water effectively. You attach a electrode lead to it, you have other leads, and now what you can do is start turning on the voltage very gradually. Okay? And that's called cyclic voltammetry. You turn on the voltage extremely gradually, and what you do is you measure the current. There's going to be a blip in the current. There's going to be a peak in the current, and that corresponds to something called the oxidation potential. Effectively, there's some current that is going to allow a chemical reaction to take place on that surface. Okay? Once you tune it to that peak current, you can keep that current at as low as possible so you don't make any other weird chemistry that's happening, and really tune it to that residue that you want. Right? And this is the ash that's been left over after the casings come out. Right?
Yep.
So you're on a low enough voltage where you're not destroying you're not causing anything else to start destroying the ash that's there. You're only tuning it barely to that
ash itself.
Okay? Barely to that ash itself. And what ends up happening is you get these two polymers called E dot and PE dot. It doesn't matter what they are. The effect is they're polymers that are long chains, but still really, really small in terms of, every day. But they're like single chemicals. And what those single chemicals are going to do is when this chemical reaction is happening, this oxidation reaction, the chemicals are going to get deposited on the ash. Okay? Oh, actually, no, sorry. They're going to get deposited on the metal, and they're going to leave the ash alone.
Okay.
Because the ash is going to be insulating.
I gotcha.
I should say that again. You stick the electrode in, you charge up the casing.
Yes.
That's going to have a bunch of carbon ash and residue on it.
Yes.
That ash is going to be insulating compared to the metal. So the chemicals are going to get deposited on the metal, but leave holes where the ash is.
It's like the opposite of the tracer stuff that they put in mice when they're trying to test them to follow it. It's like the opposite imprint of like that
exactly.
concept.
Exactly.
Like what's left is what we're looking for.
Yes, exactly. And so now we have a way of actually doing this, right? Now, why is this better than the 2008 method?
Okay, yeah.
For one, I can do this on steel.
Okay.
Right?
Yes.
I don't need the brass, zinc, and all that stuff. The other is you get a lot higher resolution on this, okay? This E.thionine method consistently yields grade 3 visualization. I didn't know this about fingerprints. With fingerprints, there's level 1 pattern, which is the fingerprint itself. The level 2 pattern is the detail on the ridges. And the level 3 pattern is within each of our ridges, there's little pores.
That's crazy.
Where the pattern of that pore is also unique to each individual.
Okay.
Right?
Yeah.
And so to really start getting something that I can admit in court and all of this other kind of stuff, it'd be really nice to get level 3 patterns, because sometimes level 2 patterns, like let's say you have just the edge of someone's fingerprint. Well, that edge could maybe match to somebody else's fingerprint and things like that. But if you have the edge of someone's fingerprint and you have the pattern of the holes, that's now extremely hard to match to erroneously.
Yeah.
Right?
Sense.
And so this current method actually lets you resolve those pores with these micro deposits, right? You've got a mechanism to now actually visualize those pores with those electrolyte contacts. And this is from the paper. You can see very clearly the pores and the ridges, right? And this is at tens of microns of resolution. That's the other key that's very different. In the 2008 method from Dr. Bond, he used a conductive powder. That powder, the size of the powder is bigger than the pores.
Yeah, that's your limiting factor for resolution.
Here we're doing single molecule deposition.
Right. So it makes total sense this is so, I'm just like bent out of shape at how clever.
Yeah.
Conceptually, like people think about this stuff.
Yeah.
It's like, why don't we put it in and then put some electrolytes around it.
Yeah.
And then we know, because we know the other aspects of this chemistry, we can just intuit, right?
Yeah. This should probably
work.
Yeah.
And then when you do it and you see the example image we just looked at,
it's a sick
where
image.
it's getting the level of detail. Oh, sorry, not this one, but number 8, where we now see in the real world that detail difference.
Yeah.
I mean, like, again, even as sort of someone who's maybe not in forensics, you could understand why you would want something with the level of fidelity on the right, versus on the left.
Yeah, exactly. And then it's pretty awesome.
It's pretty cool.
Yeah. The other cool thing that they did was actually like, so your casing goes in.
Yep.
In order to maintain a uniform electric field around that casing during this electrochemical reaction, they had a custom built cylindrical chamber that would sort of make a uniform electric field.
Okay.
Because if you put it inside a box, then the edge effects are going to be different, and you're not going to get the complete fingerprint around the thing, So now it moves to a place where, okay, if we want to implement this in industry, for each different size of casing, we should have different size chambers to actually do this reaction.
Makes sense.
The other cool thing about this is the Dr. Bond method took 2.5 kilovolts. That's not something that I can like hook up to my car battery and like, right? This thing takes less than 0.1 volts. So this could be handheld
You can have
by the crime fighting units.
Yeah. When you could do it on site, you wouldn't necessarily have to send it to a lab.
Yes. And then, with that stuff, timing is everything.
Yeah, no, that's
right?
actually a
In
really
a crime.
big deal.
So there's a lot of really new stuff that's happening. Now, before it actually gets implemented, it needs to pass something called the Doebert standard, which is the standard that they have in forensics before you can admit something in court.
Okay.
Like DNA testing had to go through this, things like that. It relies on testability. You got to have peer review. They already have peer review with this paper.
Mm-hmm.
You got to figure out what the error rates are among a general population, like not just, let's say, white males, but okay, how does it work with women? How does it work with different races?
Yep.
Things like that. And generally, to accept everything, all of these things have to be checked. So that's the next step.
It's sort of like the regulatory process or the governing standard for this moving from being something that is interesting and people could utilize but not then be admissible in court to it being able to be used to actually say, as evidence that someone is the shooter.
Yeah, exactly. And one last thing that I want to talk about is the fact that they can actually do old casings as well. They tried to do a fingerprint from a 16-month-old casing, and they were actually able to recover a fingerprint, which is, so this isn't like just now. They could be going back.
This is okay.
Yeah.
Look.
So if you thought you got away, I don't know. Yeah.
That's actually a very important detail.
Yeah.
Because it kind of, I think because, for example, if for all the fans of true crime podcasts, etc., with the advent of DNA testing, a lot of cold cases have been reopened.
Yeah.
And, people have started to, get caught for stuff they did ages ago.
Yeah.
There's another one. Another lever that could unlock a lot of stuff there.
Yeah.
I mean, there's a lot of recent cases I can think of where this existing would have been valuable. I mean, Meg the Stallion had a case with that little rapper that I can't remember his name right now, who's in jail, and like it has this issue of they fingerprinted the gun, but they not the casings that were shot.
Yeah.
And so like that would be a case where it would be interesting. Another one is obviously the recent unfortunate assassination of Charlie Kirk. Like that would be an example. Where like this would really go because there's a lot of issue about the weapon and the suspect and all of the kind of the timeline doesn't.
Yeah, quite. Yeah.
So I mean, this would be another
sell something.
Yeah, an empirical thing that would be valuable in that context.
Yeah, I think it's a very cool use of just fundamental electrochemistry for a problem that's been around for ages.
Tory Lanez. I had to say the name because I was going to be mad if I couldn't remember it. That was Megan Thee Stallion and Tory Lanez.
Yeah, okay.
I didn't forget, guys. It's a little brain fart. I got it.
I don't know who either. I don't know who either of those people are.
It's funny because it was on TikTok. It was anyway. Story number 2, our first forensic story. We should do more.
Yeah,
of those.
we should do. Yeah,
that was
that was cool.
That was a nice little true crime vibe. So again, we have now a new way to identify fingerprints from fired bullet casings. This is out of Maynooth University in Ireland, and it was in forensic chemistry. We're gonna move on to our last story. We've done a lot of health-related or healthcare-related stories, just because science is having an absolute just tear. I think on just some of these new models, new detection mechanisms, and so this last story is about Alzheimer's.
Yes,
and we have sort of it's a paper in Nature, Icahn School of Medicine at Mount Sinai, Max Planck Institute for Biology of Aging, and the University of Cologne seem to have a new detection.
Yeah, it's a new type of immune system, or it's a new type of immune cell that they found in the brain. And even that is kind of, let me be very careful. It's not a new type of immune cell because we already knew the microglia existed, but it's a state that the cell is in that is very important for mitigating Alzheimer's. And we're honing in on what exactly that cell needs to be in order to help Alzheimer's not happen.
Interesting. Okay. Got it.
Alzheimer's is an incredibly difficult disease. Okay. Incredibly difficult. There used to be this thing called the amyloid hypothesis, where the basic idea was there's a protein in our brain called beta-amyloid that misfolds, starts aggregating, and then starts creating clumps. And then those clumps are what get in the way of neurons. They start killing neurons. They start killing synapses. And then that is what leads to Alzheimer's. That's been sort of shut out by a lot of recent evidence, suggesting that that might not actually be the case. Okay.
So the hypothesis was basically there's a blockage that starts growing.
Yeah.
And then that's what impacts the brain activity, this growth of this blockage.
Exactly. And now we're slowly shifting from there's this like protein blockage to there's might be an innate immune system in the brain that might be failing at doing its job. Right?
Okay. So
that's the shift that we're sort of in the middle of actually right now as more and more papers come out.
I think I know where this is going.
Okay. And
okay.
So the core study that came out in Nature, first author Ayata, lymphoid gene expression supports neuroprotective microglia function. What they found is a novel immune-like microglial state and they've identified exactly the transcription factor that is required. They've identified exactly the genes that are involved in this microglial state. And they've identified how those genes and those transcription factors create the downstream effect of mitigating Alzheimer's. So it's top down all the way.
They have a full map.
They have a full map of how it's happening. And it's very, very cool.
Very interesting.
Okay. So let's start with Alzheimer's, right? It's an evolving landscape. Alzheimer's, 1906, described these senile plaques and neurofibrillary tangles. And the field of neurodegradation has been intellectually sort of focused on these plaques. You can see the really dark plaque in the middle of brain tissue. That's going to just get in the way of stuff, right? Then we started targeting immunotherapies that were capable of stripping the brain of these amyloid plaques, right? And those had only modest effects on cognitive decline. And that suggests that these plaques are like kind of a match that starts a much larger fire. There's something else downstream of the plaques that's really the cause.
There's something more fundamental.
Yes, exactly. And that thing that is more fundamental, people thought could be neuroinflammation, which is the inflammation of the brain because of stress, because of an immune response. Effectively, it's kind of like an autoimmune response, but local to our brain. Okay. There's the immune system itself that's supposed to be cleaning everything is now in a stage where it's just attacking all the time. Okay. So there's some genetic evidence for this because the vast majority of the late onset Alzheimer's genetic risk, like we can tell because some people have Alzheimer's and others don't. We can look at what the genetic mutations are. All of those are targeted on these things called microglia, not neurons. Okay? Those genetic loci are activated in microglia and not in neurons. So that's telling us that the riskiness of the Alzheimer's, at least from a genetic standpoint, is happening in the cells that are the microglia, not on the neurons. Right? Okay. Not on the computation, but on these housekeeping cells that might be acting up.
Yep.
Right? Microglia are a specific type of cell. They actually originate in the yolk sac, the stem cells in the yolk sac back when we're an embryo. They colonize the brain before the blood-brain barrier forms. Okay. So they get inside, and then the blood-brain barrier forms, and then they maintain themselves within the blood-brain barrier. So they don't come from the bone marrow like other immune cells do. Okay. They're sort of innate in the brain, and they stay in the brain. Okay. So another big reason why it's hard to access these things is they're inside the blood-brain barrier, right? So you can't really like poke it with drugs and things like that. And a lot of times they're basically in homeostasis. So they're doing their normal thing where they're moving around, they're cleaning up byproducts. They have these things called processes, which are, if you've ever seen immune cells like in real time, they'll like protrude out. They'll have these arms that stick out, and they're basically just surveying, right? They don't have eyes. So they're using these protrusions to increase their surface area and sense the chemical environment. And if they sense something that's bad, then they go into a state of response where they try to eat whatever thing is bad, or they try to deal with the plaques and stuff like that. But if you have too much of that, then that's going to destroy the neurons around you as well, right? So if you have too much upregulation of that state, that's pretty bad, right? And what ends up happening is you've got this aggressive amyloid deposition that happens in, let's say, mice models, right? This is something that mimics the Alzheimer's. So you've got a neuron in the middle and all of these plaques that are sort of getting in the way of the neuron trying to do everything. And if your microglial cell like actually senses some of these plaques, senses too much of the plaques, or just has this upregulation and can't downregulate, then it's a runaway reaction of immune stuff that's happening in our brain.
So what we're sort of getting at here is this idea that these immune cells might be overactivated based on some stimuli. And that overactivation is actually the driver for the neurodegeneration.
It could be one of the drivers.
One of the drivers. Of the decline in cognition, because now it's these arms that are going to pick up stuff. Are just everywhere. Doing too much. Doing too much. Picking up too many people off the street.
And when they're doing too much, they're not doing their original job. Of like cleaning the plaque and like compacting it and all this other kind of stuff.
It's like if the janitor became a vigilante at night at the building, and so instead of doing the normal janitor stuff,
now the building's
falling apart while the janitor's going to be a vigilante.
And he's not good at vigilantism either. It's like, bro. You know, so they had a bunch of different methodologies that they used, which was quite cool. They used a mouse model, and the mouse model mimics the adult Alzheimer's. They also have this Kree-Lox recombination system, which what you can do is you can induce gene deletion 4 to 6 weeks after they're born, right? Usually you imagine with gene deletion, the deletion needs to happen and then you create the life form. But then you have problems because like what if the development is perturbed, right? Then you've created this defective life form. You're making conclusions and you don't know if it's the development or the actual gene that's happening in the adult population. So here, this is a way to delay deleting a gene, and then it ensures that any phenotypes that are observed and anything that we observe in the experiment is due to a loss of gene function in the adult deceased brain, because Alzheimer's is the adult.
Yeah, right.
It's not something that,
Right.
it's this gene is doing something bad once you're getting old.
Right.
And so that's what we want to mimic. So they were able to do that. They also have this the other really cool thing that they could do was something called TRAP, which is translating ribosome affinity purification. The idea is I want to prove that the transcripts, the mRNA that's getting translated in the microglia, so the instructions from the DNA into making protein, those instructions that the microglia is paying attention to, it's coming from the actual microglia and not because the microglia is let's say, eating another immune cell, right? Because if the microglia eats another immune cell, well, that immune cell is going to have its own mRNA.
Yeah.
And when I sequence, I don't know if this mRNA came from me doing my own thing or me eating something else, and then that food is what's getting transcribed, right? So how do we make that distinction? There's this incredible way of doing it called GFP tagging, where you take this green fluorescent protein, you tag a ribosome with it. Okay, so the ribosome has attached this green fluorescent protein, and now the ribosome is going along and it's transcribing your mRNA. You take those cells in that culture, and you have another part that attaches to the GFP, that green fluorescent protein, but that thing is attached to a magnetic bead.
Oh, okay.
Okay, and now with a magnetic field, I can rip only the ribosomes from the microglia, right? Because the magnetic bead is something I can use a force on.
Right. And
the ribosome is going to have an mRNA attached, right? Because it's in the middle of doing some job.
Right.
Now all of a sudden you pick it up, so it's dragging the mRNA with it, and then you're like, okay, now I'm gonna sequence this mRNA.
Right.
That gives me an insight into the actual transcriptome of the immune cell rather than all of the mRNA in the immune cell.
That makes
right.
sense.
I'm actively looking at only the mRNA that is being transcribed into protein. That's actually being put through this machinery.
Yes.
Right. I thought that's a really cool technique.
I just the way that folks think about this as the solution to the problem, because it makes sense. You want to be able to know what is actively being translated.
Yeah. Yes.
And so you need to be able to track, in order to be able to validate, what is your process by which you can actually do validation? And it's a very clever way.
It's very clever. It's
to do that.
Yeah, basically tag the factory that's making the stuff.
Right. And so any product.
And then drag the factory out.
Right.
And then see what's inside the factory. Right? So if you want only the cars in that particular, let's say, city, and you don't want all the cars that are being ridden around by the general population, you just tag the factory, drag out the factory.
No, that's really good. That's really good.
It was very cool. So now let's get into.
It's funny they call it trap too.
Yeah, they literally call it trap. Yeah. A lot of times with these acronyms, I'm pretty sure they start with the acronym, and then they're like, okay, what are the words
100%
that can make it happen?
I like trap.
Yeah.
So
and then they put down, in the lab meeting, trap.
Translating. Okay, that works. Ribosome. There's an R.
Yeah, exactly.
So funny.
Let's get into what they actually found. Okay. They focused on a transcription factor called PU1. Okay. A transcription factor is basically something that gets attached to the DNA and promotes RNA polymerase, which is the factory that creates mRNA, to actually transcribe a gene. Okay. So this is how we get from gene to mRNA to protein. That first step, you need something called a transcription factor to get where that DNA is, bring in an RNA polymerase and be like, all right, you need to start here, look for that start codon, and then start transcribing.
The transcription factor is identifying where the things need to happen, where the polymerase needs to come in to do stuff.
Yes, and each gene usually has different transcription factors. So this particular one, this gene SPI1, has a transcription factor PU1. Okay, and different genes have different transcription factors. These transcription factors have different affinities, right? There's some that'll bind immediately. So even at low concentration, it's going to find that that bit of DNA and bind. Those are usually the housekeeping genes that you can't live without. Okay, those are the ones that like, it's like, how do I make sure that I stay alive as a cell? Okay, then there's stuff that have to do with function, specific states. Like this PU1 gene is the one that is controlling whether microglia are chilling or if they're doing the vigilante stuff, right?
Okay.
And what they found was that when microglia were in the plaque environment, that plaque environment actively enforces low PU1.
Okay.
It's very counterintuitive.
Okay.
Okay.
Yeah.
You would think that, I want like a lot of inflammation and a lot of policing around my plaques. That's not what's happening. What's happening is near the plaques, there's a downregulation of PU1, of that transcription factor, which is already a first clue that perhaps we don't fully understand this ecosystem of what's happening, right? So then they actually used a bunch of tools to figure out what is the signal transduction pathway that goes from I sense amyloid, I sense my plaques, to I downregulate PU1. And they used some knockout versions of mice to actually link all of these signal transduction pathways together. They also they also showed that there is an upregulation of a T-cell associated gene. Okay. In those low PU1 populations.
So when there's low PU, right?
Yeah.
Right. There's this there's a T-cell gene.
There's a T-cell gene
that now more frequently arises.
Yes.
Or is
yes.
Or it proliferates because of that low population environment.
Exactly. And what they think is happening is when you don't have that transcription factor, or when you don't have a lot of that transcription factor, the chromatin around that part sort of relaxes and it exposes some of the genes. And one of these genes that it exposes is CD28, which is a neuroprotective master switch. You might recognize CD28 from our Nobel Prize videos.
I was literally going to say.
Okay, CD28 is the gene that sort of regulates T cells from becoming normal T cells to T regulatory cells, right?
Yeah.
So that same gene, that same part of the gene is also having a role in microglia in the brain.
That's actually crazy.
Right? So it's like the brain is these cells are borrowing a motif from innate immunity elsewhere in the body and saying, well, I can actually use this for my own gains over here.
Right. For this function, which ultimately sort of generates this neuroprotective master switch.
Yeah.
So the idea is, because if we come back at it, because I just want to make sure I'm tracking here.
Yeah.
So we have this mechanism by which the microglia is, we don't want it when it's close to these plaque regions. It is less active.
Yeah, it's the PU1.
The PU1 is less active.
There's not enough PU1 in the cell.
Right. And that because of that induces.
Yeah, then the chromatin sort of relaxes. And now parts of the DNA get exposed, and one of the parts that gets exposed is this CD28.
And that one is sort of this is that neuroprotective master switch. Which it's so like we can it's like the Tylenol button. It's like, go fix and make all my problems go away. Right. And because of that low PU, it is what helps to release more of that.
Yeah.
And so what you don't want to happen is that process to get prevented.
Yes.
Because that is potentially then what is causing the neurodegeneration.
Exactly.
Because we're not basically releasing the Tylenol response.
Yep. Yeah. And so exactly that master switch is the switch that is controlling the cell fate of these microglia. That's turning it vigilante janitor.
That's okay. Yeah.
And so if we can control that, and we can have therapies that now that we understand this entire chain of all of the stuff that's happening, we can actually maybe do something. Right. So these microglia are now they're calling it the T-regs of the brain. T-regs being again the thing that won these 3 scientist the Nobel Prize
the military police.
Yes.
The police of the police, right? The system by which that regulates the things that regulate your body can in and of itself break down.
Exactly. And maybe that's what's happening in these Alzheimer's brains, which is causing these runaway effects that we see as symptoms. But maybe this is the cause, right? This is, or one of the causes. Obviously, Alzheimer's is extremely complicated, right?
Sure.
And there's probably multifaceted genes that are happening all in an environment. But, step by step, we're getting, closer to understanding what is really going on. And they are called the T-regs of the brain because it's very similar. They've got a very small population, just like regulatory T cells. Dominant suppressive effects, so they suppress immune responses, just like the T-regs. And then they're also dependent on the CD28, the same gene.
Yeah,
the same gene is in both. Right.
I understand the connection to T-regs because the deep dive we did for the Nobel Prize, we went really, really deep on, and it is definitely worth watching in the context of, we have so many throwback connections to past episodes in this one.
Yeah.
Because I can now much more intuitively translate in my head the idea of it being T-regs of the brain because of understanding the function of regulatory T cells and the immune response, and why a breakdown in the regulatory T cells can sort of be a driver for like problems that we see arise. So like you can map, it's a very direct,
very directly
map to this problem set. And just in terms of the framework of how to think about it.
Yep.
Obviously understanding it's a combinatorial problem set. There's multiple blah, blah, blahs.
Exactly.
But very, very interesting.
But it is very cool. And they use not only mouse models, they also had human brain tissue.
Okay.
And the same results were in the human brain tissue, which is very important. Obviously, you can't do the in vivo effects and things like that. Sure. But on the tissue, as much as you can sort of express one thing, express the other thing, all of this stuff tracks, even in humans, right? The one really cool thing that I thought they did was they used hippocampal tissue, and they looked at something called LTP, which is long-term potentiation. This is the idea that synapses will grow and shrink based on how the neurons are talking to one another. This is the physical mechanism by which we learn. Like when we say the connections are strengthening, literally what's happening is the size of the synapses, the connections, is getting bigger and smaller. It's increasing in surface area, and that's causing the connection to get strengthened. This is something that doesn't happen in Alzheimer's. Okay. So what they did was they used these brain slices. And they showed that if they have these manipulations where they downregulate PU1 using and then the CD28 comes out and stuff like that, you can restore this LTP. You can restore this ability of the hippocampus to start forming connections and have a dynamic way of expanding connections, contracting connections, so on and so forth.
That is very
so there was a mechanistic link here,
right,
to straight up learning,
right. That is tied to this,
and and the hippocampus is the center for consolidation of memories, right, and the access to the long-term memories and things like that, right. So having this happen in hippocampal slices is also super, super important to show that this could be a target for therapies in the future.
And because, the idea would be you want to try to target to the lowest level of abstraction possible.
Yeah.
And because of like this, again, analogy of T-regs for the brain, this seems to be an interesting place to target because it has so many derivative. Like it's at the foundation, and then that is going to impact processes that happen at a higher orders and all that. So that is interesting.
Yeah. So now when we look at translational horizons, it's promising, but we have to be very, very careful. Okay. One way to think about it was, what if we it depends on CD28, right? What if we just like stimulate CD28 and we boost these populations?
Yep.
That sounds simple, and biology is never that simple. There's actually this really famous disaster that happened in 2006 when it went to phase 1 trials of doing exactly this. This wasn't in the brain, but this was in the body. They were trying to stimulate CD28 to get the autoimmunity to go away and things like that, get the T-regs to come back. This was called the TGN 1412 disaster. 6 patients it resulted in cytokine release syndrome in all 6 volunteers,
Jesus.
multiple organ failures, because basically all the T cells just got activated. And then it didn't care that usually the T cell is presented with some kind of antigen, and then they act. They just like started acting.
Yeah.
And it was really bad, right? So we have to be very careful with messing with the immune system, right? And you could have something called specific antibodies, like bispecific antibodies, where it targets not just CD28, but it also targets something that is very specific to microglia, and you need both. It's an and, not an or, that like makes this thing activate.
Yep.
Perhaps that's one way of doing it. You gotta have brain penetrating vectors that go through the blood-brain barrier. That's always like iffy because now something's in my brain. I don't like the brain is. If that thing also matches in shape to some other random thing in my neurons, then what's going to happen? So, like, trying to create translational therapies is one thing, and that's its own like bag of can of worms. But understanding the mechanism itself is the first step, right? The fundamental science needs to happen first before we start saying, okay, what part of this pathway can I poke?
We have to define the treasure map, and then we can figure out the plan of how we're going to go get the treasure.
Yes.
And now we have an interesting treasure map that is specific to tissue that, again, also might have insights that are connected to other related topics. This is such a great piggyback off of our T-regs episode.
Yeah. I think it's a pretty good story, right? It shows just how complicated the brain is.
Right. Like
the brain is not just neurons, it's blood vessels, it's immune cells. Those immune cells have been there since forever, since we were born, right? All of these microglia are just hanging out in our brain. And we're not getting any new ones.
Right.
Because they can't go through the blood-brain barrier.
Right. Because it stops at some point in that development.
Yeah.
It's so good. This is so good. This was and kudos to another multi-institution Nature paper.
Yeah, multi-institution, multi-country. Yeah.
Again with Icahn School of Medicine at Mount Sinai, Max Planck Institute for Biology of Aging, and the University of Cologne. I mean, this is, again, people are working really hard. Like, obviously we lose a lot of people to Alzheimer's every year.
Yeah.
It's
the next frontier.
It's going to be hugely impactful if we can sort of take this and continue to iterate to the point where hopefully we don't want to have another TN, issue, disaster, but we have better tools now. We have better understandings.
Yeah. And I think we learned a lot from that disaster on how to start phase 1 trials for immunology. Maybe we do a lot more testing in vitro before going in vivo into a human, at least, But the other thing with this kind of stuff is it's incredibly hard to, because this is such a unique sort of late stage evolution problem. And what I mean by that is a lot of these problems with Alzheimer's is something that happens because the human brain is the most recent organ to have evolved, right? A lot of the mutations that are different, that make us different from the chimpanzees, have to do with neurodevelopment. I mean, right? But what that also means is the part of our genome and the part of our brain that is so new also means there's a lot of stuff that can go wrong, right? Because it's kind of by design. Right. We're still evolving this thing, right? All of a sudden, we kind of put evolution on pause because survival of the fittest isn't the same in the classical sense anymore. We're not having 20 kids and then the smartest ones. We're a completely different animal now. Where the evolution that's happening in humans is now not something that is in Darwin's Origin of the Species, but the genetics doesn't know that. Right. Our genome doesn't know that, and so the mutation rate is still really high, and the genome is still kind of experimenting with what the brain is doing. Right. Yep. And that's going to cause all of these failure mechanisms.
Right.
So it's really hard to find, you can't just, with heart disease, you can sometimes even take a pig's heart, put it into a human, and it'll work. Right. can't do that with the brain.
Yeah,
obviously.
right.
Right? It's like
That's actually a really good. That
like
sounds a
it's
really good
you know
point.
it's because it's by design the most recent organ. It's gonna have these failure modes that are just way more complicated than normal. Yeah.
So, and also the accessibility problem.
Yeah.
Right. Like it's kind of hard to get in there.
Yes. Yeah. Yeah.
As compared to the rest of the body. That's just another layer of
Yeah.
complexity. 3 great stories this week. We touched on a review of 3i Atlas, which was the most demanded story.
Yeah. Yeah.
And it is what
I hope you're happy now. Another Wicked reference. We got 2.
And it is very similar to what we said in our original coverage of it.
Yeah.
It's basically
It's a weird comment.
It's panned out exactly the way we described it the first time. What are the things that were going to be weird? What were the areas that still needed more information?
Yeah.
We discussed about the why we would be able to get stuff on from the Mars orbiters, why it wouldn't be that good.
Yeah, we talked about how it was
we
not,
talked about
even the guys were like, guys, you guys know it's not going to be that good, right?
we brought it up. This was months ago at this point, but again, good. Still so much to be learned.
Yeah.
We followed that up with the fingerprint story, which is so clever.
Yeah, that's clever.
That one is this clever. We can now pull fingerprints off of fired bullet casings.
Yeah.
And it works retroactively. Old stuff works for that too. So
at least 16 months.
At least 16
right?
months.
And I don't know, we haven't pushed it.
And they're going to push it.
No, they're already, yeah.
They're going to push it.
Yeah, yeah.
And then we finally ended with a great story about a better understanding of the different states that are helping us better understand how Alzheimer's, sort of the process by which it begins and a potential pathway for us to think about therapeutics to try to address what is one of the most prevalent neurodegenerative diseases that we're seeing in the human population. I'm ready for some good food this week. I'm going to eat a lot. Thanksgiving is always, my birthday is the same week as Thanksgiving. And so it's always a little bit of, I have to be thankful when we're supposed to be celebrating me.
Right. That's funny.
Like, why am this week is supposed to be about me?
Yeah.
But I get food.
They should be thankful for you.
Yeah, that's exactly right. But it'll be good.
I'm excited to travel.
You're gonna have a little
to
good time.
Hawaii.
Good time in Hawaii.
That's gonna be great.
After 3 weeks of rain here or whatever it was, it'll be nice to get to some nice weather for a little bit. As always, we really appreciate the listeners, especially those of you who get to the banter at the end, who reach us all the way here. We are going to have a couple of more episodes through the end of the year, and we may do some best of coverage for the end of year wrap up. So if you're interested in us choosing our favorite stories from the year and doing like a huge summary kind of top 10, top 5 kind of video, in the comments, wherever you see this, put bet we want to see best of.
If you made it this far, put some stuff in the comments.
Yeah.
Give us ideas for the next month.
Yeah, we want to try to do something for the holidays. We think we want to do top 10 or a top best of kind of list to wrap up the year. But let us know in the comments. I'm your host, Lester Nare, joined as always by my co-host and our resident PhD, Krishna Choudhary, for another fantastic episode. This is From First Principles.